Tonight, we're going to explore a truth that defies what your eyes tell you when you look at the night sky. The universe looks full. Stars scattered across the darkness, galaxies swirling in cosmic spirals, nebula glowing with light. But when scientists measure reality on the largest scales, they discover something terrifying. Almost everything is missing. Matter is vanishingly rare. The space between galaxies is growing faster every moment. And the forces tearing the universe apart are only getting stronger. By the end of tonight, you're going to understand why the universe is empty for a reason, what dark matter and dark energy actually do, and why this moment in cosmic history is fragile in ways most people never consider. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. Look up on a clear night away from city lights, and you'll see thousands of stars. The Milky Way stretches across the sky like a river of light. It's beautiful, and it creates an impression of abundance. All that light, all those stars. Surely the universe must be packed with matter. But here's the problem. Every single star you can see with your naked eye is in our immediate cosmic neighborhood. The farthest stars you can see without a telescope are maybe 15,000 light-years away. That sounds far. It is far by human standards, but the Milky Way galaxy is 100,000 light-years across. You're seeing less than 15% of your own galaxy, and your galaxy is just one of hundreds of billions of galaxies in the observable universe. So that sky full of stars, that's your local neighborhood. It's like standing in your backyard and assuming the entire Earth must look just like your yard. Now, let's add a telescope and see what happens. Point a powerful telescope at what looks like empty black space between stars. Choose a region with absolutely nothing visible to the naked eye, just darkness. The Hubble Space Telescope did this in 1995. They pointed the telescope at a tiny patch of sky in the constellation Ursa Major. The patch was so small, it would take 12 million such patches to cover the entire sky. In that tiny dark region, Hubble stared for 10 consecutive days. Long exposure after long exposure, gathering every photon that arrived. What did they find? Approximately 3,000 galaxies. Entire galaxies packed into a region of sky the size of a grain of sand held at arm's length. Every blob of light in that image is a galaxy containing hundreds of billions of stars. This became known as the Hubble Deep Field, and it showed astronomers something profound. Everywhere you look, even in the darkest patches of sky, there are galaxies, billions of them. They repeated the experiment in other patches of sky. Same result. Galaxies everywhere. Distant galaxies, nearby galaxies, spiral galaxies, elliptical galaxies, irregular galaxies colliding and merging. So the universe must be full, right? All these galaxies packed everywhere you look. The universe must be dense with matter. But here's where we need to do the math. Let's calculate how much matter is actually out there. The observable universe is approximately 93 billion light-years in diameter. That's the farthest we can see in any direction. Light has had 13.8 billion years to travel since the Big Bang, but the universe has been expanding that whole time. So, the sources of the oldest light are now much farther away than 13.8 billion light-year. The observable universe contains approximately 2 trillion galaxies. That's 2,000 billion galaxies. Each galaxy contains somewhere between 10 million and 1 trillion stars depending on the galaxy's size. The average is probably around 100 billion stars per galaxy. So 2 trillion galaxies times 100 billion stars per galaxy gives us roughly 200 billion trillion stars. That's 2 followed by 23 zeros. 200,000 billion stars. That sounds like a lot. It is a lot. But now let's calculate how much space those stars actually occupy. A typical star like the Sun has a diameter of about 864,000 miles. The volume of a sphere is 4/3 * the radius cubed. Plug in the Sun's radius, and you get approximately 1.4 billion miles. Now multiply by 200 billion trillion stars, and you get the total volume occupied by all the stars in the observable universe. Approximately 2.8 by 10 to the 32nd power cub miles. That sounds enormous. 2.8 followed by 32 zeros. Surely that fills a significant fraction of space. But the observable universe has a radius of about 46.5 billion light-year. Convert that to miles, and you get about 4.4 by 10 to the 26th power miles. The volume of a sphere with that radius is approximately 3.6 times 10 to the 80 power cub miles. Compare those numbers. Stars occupy about 2.88 by 10^32 power cub miles. The universe has a volume of about 3.6 by 1080 power cub miles. Divide the first by the second, and you get the fraction of space occupied by stars. Approximately 7.8 by 10 to the -49th power. That's 0.0000000078 stars occupy less than 1 quadrillionth of 1 quadrillionth of 1 quadrillionth of a percent of space. Let me put that in perspective. If you shrank the observable universe down to the size of Earth, all the stars combined would occupy a volume smaller than a single atom. Actually, much smaller than a single atom. More like a single proton. And that's just stars. Most of a star's volume is empty space, too. The nucleus of an atom occupies about 1 trillionth the volume of the atom. The rest is empty space where electrons orbit. So even the matter in stars is mostly emptiness. And we haven't even talked about the space between stars within galaxies, or the space between galaxies yet. The Milky Way galaxy contains approximately 200 billion stars. The galaxy is about 100,000 light-years across. That's roughly 588 trillion miles. The nearest star to the Sun, Proxima Centauri, is about 4.2 light-years away. That's roughly 25 trillion miles. So the distance between stars is thousands of times larger than the stars themselves. If you scaled the Sun down to the size of a grain of sand 1 millimeter across, the nearest star would be about 19 miles away, 30 miles of empty space between 2 grains of sand. That's the typical spacing within our galaxy. And galaxies themselves are separated by even more dramatic distances. The Andromeda Galaxy, our nearest large neighbor, is about 2.5 million light-years away. The Milky Way is 100,000 light-years across. So, the distance to Andromeda is 25 times the width of the Milky Way. That's like 2 grains of sand separated by a football field if we're keeping our scale. And between the Milky Way and Andromeda, there are only a handful of smaller dwarf galaxies. Mostly, it's just empty space, nothing. Vacuum, darkness. And this is in our local group, one of the denser regions of the universe. In other regions, galaxies are much farther apart. Clusters of galaxies are separated by even larger voids containing almost nothing. So, the universe is mostly empty space between stars with more empty space between galaxies, with even more empty space between galaxy clusters. But we're not done yet, because there's a deeper problem. Even counting all the stars and all the galaxies and all the gas and dust between them, we're still missing most of the universe. In the 1930s, Swiss astronomer Fritz Zwicky was studying the Coma galaxy cluster. This is a large group of galaxies about 320 million light-years away. Zwicky measured how fast the galaxies in the cluster were moving. He knew the cluster was held together by gravity with all the galaxies orbiting a common center of mass. From the galaxy's speeds, he could calculate how much total mass must be present to generate enough gravity to hold them together. Then he looked at the galaxies themselves. He counted them, measured their brightness, estimated their mass based on how much light they emitted, and he discovered a problem. The galaxies weren't massive enough. Not even close. Based on visible matter, the cluster should fly apart. The galaxies were moving too fast to be held together by the gravity of visible matter alone. Zwicky calculated that the cluster needed about 400 times more mass than he could see. He proposed that most of the mass must be dark, invisible matter that doesn't emit light. He called it dark matter. Nobody believed him. Dark matter sounded absurd. Invisible matter that somehow had mass, but didn't interact with light. It violated common sense. Scientists looked for other explanations. Maybe Zwicky made a mistake in his measurements. Maybe the galaxies weren't actually gravitationally bound. Maybe our understanding of gravity was wrong on large scales. But as more observations came in over the following decades, the problem persisted. In the 1970s, astronomer Vera Rubin studied the rotation of spiral galaxies. She measured how far stars orbit the galactic center at different distances. In our solar system, planets closer to the Sun orbit faster than planets farther out. Mercury orbits faster than Earth. Earth faster than Mars. Mars faster than Jupiter. This makes sense because gravity weakens with distance. The farther you are from the Sun, the weaker its gravitational pull, the slower your orbit. Galaxies should work the same way. Stars near the galactic center should orbit faster than stars in the outer regions. But that's not what Rubin observed. She found that stars in the outer regions of galaxies orbit just as fast as stars closer to the center, sometimes even faster. This made no sense. Unless there was additional mass in the outer regions, providing extra gravitational pull, mass that wasn't visible. Rubin's observations confirmed Zwicky's finding. Galaxies contain far more mass than we can see. The visible stars and gas make up only about 15% of a galaxy's total mass. The other 85% is dark matter. And it's not just galaxies. Dark matter shows up everywhere astronomers look. In galaxy clusters, in the cosmic web, in the rotation of galaxy groups, in gravitational lensing measurements, in the cosmic microwave background radiation patterns. Every independent measurement points to the same conclusion. Most of the matter in the universe is invisible. We can't see it. We can't touch it. It doesn't emit light or absorb light or interact with electromagnetic radiation in any way. But it has mass. It curves spacetime. It exerts gravitational pull, and it outweighs normal matter by a factor of about 6 to 1. For every kilogram of normal matter, protons and neutrons and electrons, the stuff that makes up atoms and molecules and stars and planets and people, there are approximately 6 kilograms of dark matter. So when we calculated earlier that stars occupy a tiny fraction of space, we were only counting normal matter. Dark matter takes up even more volume, though we can't see it directly. Current estimates suggest dark matter makes up about 27% of the universe's total mass energy content. Normal matter, everything we can see and touch, makes up about 5%. That means 95% of the universe's mass energy is in forms we don't fully understand. Let's talk about what dark matter actually does, because this is crucial to understanding why galaxies exist at all. Without dark matter, galaxies as we know them couldn't form. The gravity from normal matter alone isn't strong enough to pull gas together into the dense clumps needed for star formation. Here's how it works. In the early universe, hydrogen and helium gas was spread fairly uniformly throughout space. To form galaxies, this gas needed to collapse under gravity into dense clouds. But normal matter interacts with radiation. As gas clouds collapse and heat up, they emit radiation. This radiation carries energy away, but it also creates pressure that resists further collapse. The gas wants to collapse under gravity, but radiation pressure pushes outward, preventing collapse. This creates a balance that's very difficult to overcome with normal matter alone. Dark matter solves this problem. Dark matter doesn't interact with radiation. It doesn't emit light, doesn't absorb light, doesn't feel radiation pressure. So dark matter can collapse freely under gravity without any resistance from radiation. In the early universe, dark matter formed the scaffolding, the framework of structure. Dark matter clumped together first, forming halos, spherical clouds of dark matter held together by their own gravity. These dark matter halos created gravitational wells, deep pits in the fabric of spacetime. Normal matter, hydrogen and helium gas fell into these gravitational wells. Once the gas was concentrated by falling into the dark matter halo, it could collapse further and begin forming stars. So, every galaxy has a dark matter halo surrounding it. The visible galaxy, the stars and gas we can see, sits at the center of a much larger dark matter halo. The Milky Way's visible disk is about 100,000 light-years across. But its dark matter halo extends at least 600,000 light-years, possibly farther. That's 6 times larger than the visible galaxy. And the dark matter halo contains about 10 times as much mass as all the stars and gas in the visible galaxy combined. So when you look at an image of the Milky Way, you're seeing less than 10% of the galaxy's total mass. The rest is invisible dark matter surrounding the visible parts. Every galaxy we observe has this structure: a visible component made of stars and gas, and a much larger invisible component made of dark matter. The dark matter dominates the galaxy's gravity, determining how far stars orbit and how the galaxy interacts with neighbors. Astronomers can map dark matter halos by measuring how galaxies rotate. In the outer regions of galaxies far from the visible edge, there are still gas clouds and a few stars. By measuring how fast these objects orbit, astronomers can determine how much total mass is present. And consistently they find far more mass than can be accounted for by visible matter. This extra mass has a characteristic distribution. It's densest at the center and gradually becomes less dense moving outward. The density drops off much more slowly than the density of visible matter. Visible matter is concentrated in the galactic disk. Dark matter is spread throughout a spherical halo. This difference in distribution is part of what convinced astronomers that dark matter must be something fundamentally different from normal matter. It's not just dark clouds of normal matter, not planets or failed stars or dust. It's something else entirely. Scientists have built sensitive detectors deep underground trying to catch dark matter particles. The detectors are underground to shield them from cosmic rays and other interference. They're looking for extremely rare events where a dark matter particle passes through the detector and collides with a normal atom. Such collisions should be incredibly rare because dark matter barely interacts with normal matter. But if you have a large enough detector and wait long enough, you might detect a few events. So far, these experiments have found nothing conclusive. There have been hints, possible signals that might be dark matter, but nothing confirmed. Other experiments are searching for dark matter at particle colliders, like the Large Hadron Collider. The idea is to create dark matter particles by smashing normal particles together at extremely high energies. If dark matter particles are created in these collisions, they would fly out of the detector without leaving a trace because they don't interact with normal matter. But their existence would be inferred from missing energy and missing momentum. The collision's total energy and momentum must be conserved. If some energy and momentum disappears, it must have been carried away by something invisible. That something could be dark matter. Again, no confirmed detection yet. We have several theories about what dark matter might be. The leading candidate is called weakly interacting massive particles, or WIMPs. These would be subatomic particles heavier than protons, but interacting only through gravity and the weak nuclear force. The weak nuclear force is responsible for certain types of radioactive decay. It's extremely weak, hence the name, operating only over distances smaller than an atomic nucleus. If dark matter particles interact through the weak force, they would be almost impossible to detect directly, but would still have mass and create gravitational effects. WIMPs would have been created in the early universe when temperatures were high enough for their formation. As the universe cooled, WIMP creation stopped, leaving a certain amount frozen into existence. Calculations suggest that if WIMPs exist with certain properties, they would naturally make up about 27% of the universe's mass energy, exactly matching observations. This remarkable coincidence is called the WIMP miracle, and it's why WIMPs are considered the leading dark matter candidate. But WIMPs haven't been detected despite decades of searching. This has led some physicists to consider alternatives. Axions are another candidate. These are hypothetical particles much lighter than WIMPs, possibly 1,000,000 times lighter than electrons. Axions were originally proposed to solve a different problem in particle physics, but they could also account for dark matter. If they exist, there would need to be enormous numbers of them to make up the required mass. But because they're so light, they would behave differently from WIMPs, forming structures on different scales. There's also primordial black holes. These are black holes that formed in the early universe from density fluctuations, not from collapsing stars. If enough primordial black holes formed with the right mass range, they could account for dark matter. They would have mass. They would create gravitational effects, and they wouldn't emit light. But there are observational constraints that make this unlikely. We don't see the gravitational lensing effects that large numbers of black holes would produce. Some physicists have even proposed that there is no dark matter, and instead our understanding of gravity is wrong on large scales. This approach is called modified Newtonian dynamics or MOND. The idea is that gravity doesn't follow Newton's inverse square law exactly when gravitational fields are very weak. In galaxy-scale gravitational fields, gravity might be stronger than Newton predicts, eliminating the need for dark matter. MOND can explain galaxy rotation curves fairly well, but it struggles to explain other observations, like galaxy clusters and gravitational lensing and the cosmic microwave background patterns and find. Most physicists favor dark matter over modified gravity, because dark matter explains more observations more consistently. But until we detect dark matter directly, modified gravity remains a possibility. The point is we know dark matter exists because we can measure its gravitational effects, but we don't know what it is. It could be WIMPs or axions or primordial black holes, or something we haven't thought of yet. This is one of the biggest unsolved mysteries in physics. We're trying to understand what constitutes 27% of the universe's mass, and we have no confirmed answer. And this mystery makes the universe feel even emptier. Not only is space mostly vacant, but most of the matter that does exist is invisible and unknown. We're surrounded by dark matter right now. It's passing through you constantly. Hubble also measured the red billions of dark matter particles flowing through the Earth, which tell you how fast they're receding through your body every distance versus recession velocity. You don't feel it because it doesn't interact linear electromagnetically. It doesn't collide with the atoms in your body in any meaningful way. Galaxies three times farther away you're not receding 3 times as fast. This was revolutionary. Before Hubble, most astronomers thought the universe was static, eternal, unchanging. Some galaxies were moving toward us, some away. But the universe as a whole wasn't going anywhere. Hubble's observations showed that wasn't true. Every galaxy in every direction was moving away from us. And the more distant the galaxy, the faster it was receding. The only explanation was that the universe itself is expanding. Space is growing, carrying galaxies apart. The rate of expansion is described by the Hubble constant. This is the ratio of recession velocity to distance. Current best measurements put the Hubble constant at approximately 43.5 meters per second per megapark. Megapark is roughly 3.3 million light-years. So for every 3.3 million light-years of distance, recession velocity increases by 43.5 meters per second. A galaxy 10 megaparsecs away recedes at 435 meters per second. A galaxy 100 megaparsecs away recedes at 4,350 meters per second. A galaxy 1,000 megaparsecs away recedes at 43,500 meters per second, and so on. At some distance, the recession velocity reaches the speed of light. This happens at approximately 14 billion light-years in the current universe. Beyond that distance, galaxies are receding faster than light. This doesn't violate relativity, because they're not moving through space faster than light. Space itself is expanding faster than light can traverse it. Light leaving a galaxy receding faster than light will never reach us. It's emitted in our direction, but space is expanding between us, and that light faster than the light can cross it. The light makes progress, but the distance it needs to cross increases faster than it can travel. It's like swimming upstream in a current faster than you can swim. You're making forward progress through the water, but the water is carrying you backward faster. So you move backward overall. Light from these distant galaxies is carried away from us by expansion despite traveling toward us through space. This defines the edge of the observable universe, the cosmological horizon. Objects beyond this horizon are causally disconnected from us. We can never observe them, never interact with them, never receive information from them. They exist presumably, but they're forever beyond our reach. And here's the critical point. This horizon is moving inward over time. As the universe continues expanding, and that expansion accelerates due to dark energy, more and more galaxies cross the horizon and disappear from view. Right now, we can see galaxies about 46.5 billion light-years away in any direction. That's the current radius of the observable universe. But many of those galaxies are already receding faster than light. We see them only because the light we're receiving left those galaxies billions of years ago, when they were closer, and when expansion was slower. The light that's leaving those galaxies now will never reach us. And galaxies that are currently within our observable universe, but near the edge, will eventually cross the horizon as expansion continues. Let's trace what happens to a specific galaxy over time. Consider a galaxy currently 10 billion light-years away. That galaxy is receding from us at approximately 435,000 meters per second. That's more than twice the speed of light. We can see this galaxy because we're receiving light that left it 10 billion years ago, when it was much closer. But that galaxy is now crossing, or has already crossed, our cosmological horizon. In the far future, light from the galaxy will be so redshifted that it becomes undetectable. The wavelengths will stretch to meters, miles, eventually light-years. The photons will have so little energy they might as well not exist. And new light leaving the galaxy will never reach us at all. From our perspective, that galaxy fades away and disappears. Now consider galaxies that are currently closer, say 5 billion light-years away. These galaxies are receding slower, maybe 217,000 meters per second. Still faster than light, but less extreme. We can observe these galaxies fairly easily with modern telescopes. But over time, as expansion continues and accelerates, these galaxies will also recede faster and faster. Eventually, they too will cross the horizon. The observable universe is shrinking from the outside in. The most distant galaxies disappear first, then slightly closer ones, then closer still. Given enough time, only our local group remains visible. But there's a limit to this shrinkage, because gravity holds structures together. Objects that are gravitationally bound don't participate in cosmic expansion. The Milky Way and Andromeda are gravitationally bound, moving toward each other on a collision course. The expansion of space has no effect on this because gravity is stronger than expansion on this scale. Our local group contains about 80 galaxies, all gravitationally bound. They will eventually merge into a single large elliptical galaxy over the next several billion years. This merged galaxy will remain intact despite cosmic expansion because it's held together by its own gravity. Similarly, our local supercluster, the Lania supercluster, contains about 100,000 galaxies. Gravity binds this structure loosely. Some parts of it may remain gravitationally connected over time. But beyond the supercluster scale, expansion dominates. Galaxy clusters not bound to our supercluster are being carried away. The Virgo cluster, the Forix cluster, the Coma cluster. All these structures are receding from us. Over tens of billions of years, they'll cross the horizon and disappear. Eventually, observers in what remains of our local group will look out and see only their own merged galaxy. Maybe a few satellite dwarf galaxies if they remain bound, but everything else will be gone, carried beyond the horizon by accelerating expansion. The cosmic microwave background will also fade. Right now, the CMB is detectable as microwave frequency radiation at 2.7 Kelvin. But as space expands, this radiation gets redshifted to longer wavelengths and lower energies. Over trillions of years, it will be redshifted into radio waves, then even longer wavelengths. The temperature will drop below 1 Kelvin, below 0.1 Kelvin, approaching absolute zero. Eventually, it will be so diffuse and low energy that it's undetectable with any conceivable technology. The CMBB, the most direct evidence we have of the Big Bang, will be erased by expansion. Future civilizations won't be able to observe it. They won't know the universe had a hot, dense beginning. They might develop physics and chemistry and understand stars and planets. But cosmology, as we know it, would be impossible. They'd have no way to discover the Big Bang, no way to measure cosmic expansion, no way to infer the universe's history. They'd be observationally isolated, trapped in a single galaxy or small group of galaxies, with no evidence that anything else ever existed. This has led some physicists to wonder what we might be missing. Are there aspects of cosmology that we can't access because they've already been erased by expansion? Were there structures or events in the very early universe that we have no evidence for because all traces have been redshifted beyond detection? Possibly we can observe back to the cosmic microwave background which formed about 380,000 years after the Big Bang. Before that, the universe was opaque to light, too hot and dense for photons to travel freely. So, we have no direct optical observations of the first 380,000 years. We can infer what happened using physics and theory, but direct observation is impossible. Could there have been interesting structure or events during that time that left no observable traces? We might never know. Similarly, there might be structures or phenomena beyond our current cosmological horizon that we have no way to detect. The observable universe might be a tiny fraction of the total universe. Everything beyond our horizon is unknowable to us. This is humbling. We can map and measure and understand the observable universe. But we have to accept that this might be only a small sample of all that exists, and that sample is shrinking over time as more objects cross the horizon. The universe we can observe is getting smaller, while the total universe continues getting larger. Our window on reality is closing. In this context, we're fortunate to exist now in an era when the universe is still observable, when distant galaxies are still visible, when the CMEB is still detectable, when we can still measure expansion and infer the Big Bang. A few trillion years from now, this won't be possible. Future civilizations will have less information than we do. They'll inherit a lonelier, darker universe. And this raises profound questions about our place in cosmic history. Are we early or late in the universe's timeline? The universe is approximately 13.8 billion years old. Stars will continue forming for at least 100 trillion years, possibly much longer. So, we're only about 0.01% of the way through the stelliferous era. We're incredibly early. Most of the stars that will ever exist haven't formed yet. Most planets haven't formed. Most opportunities for life haven't happened yet. We might be among the first civilizations to arise in the universe. Or we might not. Perhaps intelligent life is common and we're typical. Perhaps it's rare and we're unusual. We don't know. But what we do know is that we exist at a time when the universe is maximally observable. In the deep past, the universe was too hot and dense for structure. In the deep future, it will be too empty and dark for cosmology. Right now, we're in the sweet spot. And that's not a coincidence. Life requires certain conditions. Stars, planets, stable environments, billions of years of evolution. These conditions exist during the stelliferous era when the universe has cooled enough for structure but hasn't expanded so much that structure is isolated. So intelligent life, wherever it arises, will tend to find itself in this same sweet spot. This is a form of selection bias called the anthropic principle. We observe the universe to be in a life-friendly state because we couldn't exist to observe it otherwise. If the universe were too young, too hot, too dense, we wouldn't be here. If it were too old, too cold, too empty, complex structures like life probably couldn't form. So our existence at this particular time is not random. It's a consequence of the conditions required for life. But even within this stelliferous era, there's a narrower window for cosmology. Right now, we can see distant galaxies and the CMB. In a trillion years, distant galaxies will be gone and the CMB will be faint. In 10 trillion years, cosmology will be nearly impossible. So there's a brief period, cosmologically speaking, when the universe is both observable and inhabited by intelligence. We're in that period now, and what we're observing is a universe becoming emptier. But let's return to the present and talk about why the universe is empty in the first place. Why isn't space filled with matter? Why are galaxies so far apart? Why is dark matter spread so thin? The answer lies in the early universe and the processes that created all structure we see today. In the first moments after the Big Bang, the universe was incredibly dense and hot. All the matter and energy that would eventually form galaxies and stars and planets and us was compressed into an unimaginably small volume. We're talking about the entire observable universe. 93 billion light-years across today, compressed to a size smaller than an atom. Temperature was beyond anything we can create or even imagine. At 1 second after the Big Bang, temperature was approximately 10 billion Kelvin. At 1 millisecond after the Big Bang, 1 trillion Kelvin. At 1 microsecond after the Big Bang, 10 trillion Kelvin. Go back farther, and the temperature was even higher, reaching energies where our current physics breaks down. At these temperatures, matter as we know it couldn't exist. No atoms, no molecules, not even protons or neutrons. Just a soup of fundamental particles and energy, quarks and gluons and electrons and photons, all interacting violently in an incredibly dense, incredibly hot plasma. This state lasted only a tiny fraction of a second. As the universe expanded, it cooled rapidly. At about 1 microsecond old, quarks combined to form protons and neutrons. At about 3 minutes old, protons and neutrons combined to form the first atomic nuclei, mostly hydrogen and helium. At about 380,000 years old, the universe cooled enough for electrons to combine with nuclei, forming the first atoms. This moment is called recombination. Before recombination, the universe was opaque to light. Photons couldn't travel freely because they constantly scattered off free electrons. After recombination, When electrons were bound into atoms, photons could travel freely. The universe became transparent. The photons that were freed at recombination are what we see today as the cosmic microwave background. They've been traveling through space for 13.8 billion years, redshifted by expansion from visible light to microwaves. The CMB gives us a snapshot of the universe at age 380,000 years. And what that snapshot shows is that the universe was remarkably uniform at that time. The temperature varies by only about 1 part in 100,000 across the sky. Some regions were slightly hotter, slightly denser than average. Other regions were slightly cooler, slightly less dense. But these variations were tiny, much smaller than the variations we see today. This uniformity is puzzling. How could regions of space billions of light-years apart have almost exactly the same temperature? They couldn't have been in thermal contact, couldn't have exchanged heat to equilibrate. Light hasn't had time to travel between them even now, let alone in the early universe. The solution is called cosmic inflation. This is the idea that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. Space expanded faster than light, doubling in size many times over an incomprehensibly short period. Different models of inflation predict different details, but the basic idea is that in roughly 10 to the minus 32 power seconds, the universe expanded by a factor of at least 10 to the 26 power. That's doubling about 87 times in a time so short it's essentially meaningless to human comprehension. For comparison, there are roughly 10 to the 18th power seconds in the entire age of the universe. The inflation period was 10 to the minus 32 power seconds. That's 1 million trillion times shorter than the universe's current age. And in that incomprehensibly brief moment, space expanded by a factor of at least 100 million trillion. The observable universe today, 93 billion light-years across, was smaller than a proton before inflation. After inflation, it was roughly the size of a grapefruit or basketball, depending on the model. Then inflation ended and normal expansion took over, gradually increasing size over the next 13.8 billion years to reach the current scale. Why did inflation happen? We don't know for certain. The leading idea is that it was driven by a field called the inflaton field, which filled all of space. This field had potential energy like a ball sitting on top of a hill. The ball wants to roll down to the bottom of the hill, but it's stuck at the top temporarily. Similarly, the inflaton field was stuck in a high energy state. And while it was stuck, its energy caused space to expand exponentially. Eventually, the field rolled down to a lower energy state. Inflation ended, and the field's energy converted into particles and radiation, heating the universe back up. This reheating created all the matter and energy we see today. So in a sense, inflation borrowed energy from empty space, used it to inflate space exponentially, then converted it into matter when inflation ended. Inflation solves several problems in cosmology. It explains why the universe is so uniform. Before inflation, the entire observable universe was a tiny region small enough to be in thermal equilibrium. All parts were in contact, could exchange heat, reach the same temperature. Then inflation stretched this tiny uniform region to enormous size. The uniformity was preserved, stretched out with the space. That's why the CMB looks so uniform today. Inflation also explains why the universe is so flat geometrically. General relativity allows 3 possible geometries for the universe. Positive curvature, like a sphere surface where parallel lines eventually converge. Negative curvature, like a saddle surface where parallel lines diverge. Or flat, like a plane surface where parallel lines stay parallel. Measurements show the universe is flat to high precision. But flatness is unstable. If the universe started with even tiny curvature, expansion would amplify it over time. A slightly curved universe would become more curved as it expands. For the universe to be flat today, it must have been incredibly precisely flat at the beginning. This seemed like an improbable fine-tuning. Inflation solves this because exponential expansion stretches out curvature. Any initial curvature gets inflated away, flattened to near zero. The observable universe becomes so large that any curvature is negligible within the observable region. It's like zooming in on a sphere's surface. At small scales, a sphere looks curved, but zoom in close enough and any small patch looks flat. Inflation zoomed in on the universe, making the observable region a tiny patch of something much larger. Within that patch, curvature is undetectable. But inflation's most important contribution for our purposes is that it created the seeds of all structure. The inflating field was subject to quantum fluctuations. At quantum scales, fields don't have precise values. They fluctuate randomly due to the Heisenberg uncertainty principle. Normally, these fluctuations are tiny and irrelevant. But during inflation, these quantum fluctuations were stretched to cosmic scales. A quantum fluctuation smaller than a proton got inflated to the size of a galaxy or larger. These stretched quantum fluctuations became density variations in the early universe. Regions where the inflating field happened to have slightly more energy became slightly denser after inflation ended. Regions with slightly less energy became slightly less dense. These density variations were imprinted on the matter and radiation when the inflating field decayed, and they're what we see today as the CMED temperature variations. 1 part in 100,000 differences in density doesn't sound like much, but gravity amplifies density differences over time. A region that's slightly denser than average has slightly more gravity. This attracts nearby matter, making the region denser still, which increases gravity further, attracting more matter. Positive feedback. Over hundreds of millions of years, regions that started only 1 part in 100,000 denser collapsed into the first galaxies. The first stars formed in these galaxies, probably about 100 million years after the Big Bang. These were massive stars, hundreds of times the mass of the Sun, burning bright and dying young in supernova explosions that scattered heavy elements into space. Later, generations of stars formed from gas, enriched with these heavy elements. Galaxies grew by accretion, gradually pulling in more gas and forming more stars. They also grew by mergers, colliding and combining with other galaxies. The cosmic web structure emerged as matter flowed from under dense regions toward over-dense regions. Filaments formed connecting galaxy clusters. Voids emptied out as matter drained toward filaments. By about 1 billion years after the Big Bang, the large-scale structure was beginning to resemble what we see today. The initial density variations were incredibly small, 1 part in 100,000. If they had been exactly zero, perfectly uniform, structure could never form. Gravity would have nothing to work with. Matter would remain uniformly spread as the universe expanded. No galaxies, no stars, no planets, no life, just a thin gas of hydrogen and helium spreading ever thinner as space expands. But equally, if the density variations had been much larger, say 1 part in 1,000 instead of 1 part in 100,000, gravity would have been too strong. Dense regions would have collapsed too quickly and violently. Instead of forming galaxies, they would have formed black holes directly. The universe would have been full of black holes soon after the Big Bang, with no opportunity for stars or planets to form. So the amplitude of the density fluctuations had to be just right, large enough for structure to form, small enough that structure forms gradually, allowing stars and galaxies instead of just black holes. This fine-tuning is part of why the universe is as empty as it is. If density fluctuations had been larger, more matter would have clumped together. Galaxies would be more common, closer together. Space between them would be less empty. But then conditions wouldn't be right for star formation and life. If density fluctuations had been smaller, less matter would have clumped together. Galaxies would be rarer, farther apart. Space would be even emptier than it is. And again, conditions wouldn't be right for star formation and life. We observe the universe to have this particular level of emptiness because it's the level compatible with our existence. Too full and black holes dominate. Too empty and galaxies don't form. Just right, and we get galaxies and stars and planets and life. This is another manifestation of the anthropic principle. The universe's emptiness is a consequence of the conditions required for observers to exist. So when we ask why the universe is so empty, part of the answer is that it couldn't be much different and still produce structures like us. But there's more to the story. The density fluctuations determine the initial distribution of matter, but expansion determines how much that matter spreads out over time. And this is where dark energy becomes crucial. In a universe without dark energy, just matter and radiation expansion would gradually slow down over time. Gravity would work to pull everything back together. The universe might eventually stop expanding and recollapse in a big crunch. Or it might expand forever, but at an ever-decreasing rate, gradually approaching zero expansion. In either case, the relative distances between structures would remain roughly constant or decrease. Galaxies that are close now would stay close or get closer. The cosmic web structure would persist or even strengthen over time as gravity pulls filaments and clusters together. But we don't live in that universe. We live in a universe dominated by dark energy. And dark energy causes expansion to accelerate. This changes everything. Instead of gravity gradually winning, pulling structures together, expansion is winning, pulling structures apart. The cosmic web is being stretched, filaments are thinning, voids are growing, and this process is accelerating over time. Dark energy's density appears to be constant or nearly constant as space expands. This means as the universe grows larger, there's more total dark energy. Meanwhile, the density of matter decreases as space expands because the same amount of matter is spread over larger volume. So, dark energy's influence grows stronger relative to matter's influence as time passes. In the early universe, matter dominated. The universe was dense enough that matter's gravity overwhelmed dark energy's repulsion. Expansion was decelerating, slowing down due to matter's gravity. This allowed structures to form. Overdense regions could collapse under gravity because expansion wasn't too fast. Matter had time to flow from underdense regions to overdense regions, creating the cosmic web. But about 5 billion years ago, dark energy began to dominate. The universe had expanded enough that matter became sufficiently dilute. Dark energy's constant density meant it now contributed more to the total energy density than matter. Expansion began accelerating, and it's been accelerating ever since. This acceleration is destroying structure gradually. Objects not gravitationally bound are being pushed apart faster and faster. In the far future, the universe will be much emptier than it is now. Most matter will be concentrated in isolated galaxy clusters or individual merged galaxies separated by voids billions or trillions of light-years across. The cosmic web will be gone, stretched out of existence. Eventually, over time scales beyond easy comprehension, dark energy might overcome even gravitational binding. There's a scenario called the Big Rip, where dark energy's density increases over time instead of remaining constant. If this happens, expansion accelerates more and more until it tears apart even bound structures. First, galaxy clusters dissolve, then individual galaxies, then stellar systems, then planets, then molecules, atoms, atomic nuclei. Everything gets ripped apart by exponentially increasing expansion. The universe ends not in fire or ice, but in being torn to pieces at every scale. This is speculative, and most physicists don't think it's likely, but it's possible. If dark energy behaves in certain ways, we haven't ruled out. More likely, dark energy's density remains constant, and the universe simply expands forever with constant acceleration. This leads to heat death. A cold, dark, empty future where all structures have dissolved and all energy has dissipated. But that's trillions of years away. For now, we live in a universe that's empty but not yet maximally empty, where structure exists but is gradually dissolving, where galaxies shine but are slowly being isolated from each other by expanding space. And it's getting worse. As the universe continues to expand and dark energy drives accelerating expansion, structures are being pulled apart. Galaxies that are not gravitationally bound are receding from each other faster and faster. Galaxy clusters are becoming more isolated. Superclusters are dissolving. The cosmic web is being stretched with filaments thinning out and voids growing larger. Eventually, over time scales of hundreds of billions or trillions of years, even gravitationally bound structures might be affected. If dark energy continues to dominate, and its density remains constant or increases, it could eventually overcome gravity on smaller and smaller scales. First, it would dissolve superclusters, then galaxy clusters, then galaxy groups. Eventually, it could even tear apart individual galaxies, pulling stars away from each other. In the most extreme scenario called the Big Rip, dark energy would eventually overcome even the forces holding atoms together. Molecules would be torn apart, then atoms, then atomic nuclei, then even quarks within protons and neutrons. The universe would be ripped apart on every scale from largest to smallest until nothing remains but isolated particles spreading through infinite space. This is speculative. We don't know if dark energy will remain constant or increase or decrease over time, but current evidence suggests it's at least constant, which means the universe will continue expanding forever. Structures will continue dissolving and emptiness will continue to grow. The universe's fate appears to be heat death. Let me explain what heat death means in detail because it's both the most likely future and the most profound. Heat death doesn't mean the universe gets hot. It means the universe reaches thermal equilibrium, a state where all energy is evenly distributed and no more work can be done. Imagine a cup of hot coffee in a room. The coffee is hotter than the room. So, heat flows from coffee to room. Over time, the coffee cools down and the room warms up slightly until they reach the same temperature. At that point, no more heat flows. The system has reached thermal equilibrium. The coffee and room still have energy, but that energy is now evenly distributed. No differences in temperature, no gradients, no way to extract useful work from the system. The universe is heading toward the same fate on an incomprehensibly larger scale and longer time scale. Right now, the universe is far from equilibrium. Stars are hot. Space is cold. Galaxies are dense. Voids are empty. There are gradients everywhere. Differences in temperature and density and energy. These differences allow things to happen. Stars burn, planets orbit, galaxies evolve, life exists. All of it depends on being out of equilibrium, on having energy concentrated in some places and not others. But the second law of thermodynamics says entropy always increases in a closed system. Entropy is a measure of disorder of how spread out energy is. High entropy means energy is evenly distributed. Low entropy means energy is concentrated. The universe started in a low entropy state with energy concentrated in the Big Bang. As time passes, entropy increases. Energy spreads out. Differences fade, and this process continues until everything reaches equilibrium. When that happens, the universe will be in a state of maximum entropy. Maximum disorder, maximum emptiness in a sense because no concentrated structures remain. Let's trace this process over deep time. We're currently about 13.8 billion years into the universe's history. For the next 100 trillion years or so, stars will continue forming from gas in galaxies, not at the same rate as now. Star formation is already declining, and will continue to slow as gas is used up or expelled from galaxies. But there's enough gas that small red dwarf stars, the longest-lived type, will keep forming for at least 100 trillion years. So for the next 100 trillion years, the universe will still have stars shining, planets orbiting, potentially life evolving. This is called the stelliferous era, the age of stars. We're about 0.01% through this era. Most of it lies ahead, but eventually the gas runs out or becomes too dispersed for new stars to form. By about 100 trillion years from now, star formation will essentially cease. From that point forward, only existing stars remain, slowly burning out. Red dwarf stars, the smallest stars that can sustain fusion, live for trillions of years. Some red dwarfs born today will still be shining 100 trillion years from now. But one by one, they'll exhaust their hydrogen fuel and die. A red dwarf becomes a white dwarf, a hot, dense remnant about the size of Earth, containing the star's leftover mass. White dwarfs don't burn fuel. They just cool down gradually over trillions of years, radiating away their remaining heat. By about 10 to the 15 power years from now, 10 quadrillion years, all stars will have died. No more fusion, no more starlight. The universe enters what's called the degenerate era, named after the quantum degenerate matter that makes up white dwarfs. At this point, the universe contains mostly white dwarfs, neutron stars from supernovas, and black holes from collapsed massive stars. There are also brown dwarfs, failed stars that never ignited fusion, slowly cooling, and planets no longer orbiting stars, but drifting through space or orbiting white dwarfs. Everything is dark and cold. White dwarfs and neutron stars still glow faintly from residual heat, but that heat gradually radiates away. Eventually, over time scales of 10 to the 30 power years, all these objects will cool to near absolute zero. They'll become black dwarfs, cold, dark remnants with no internal heat. During this time, another process is occurring. Gravitational interactions between objects in galaxies or galaxy remnants will gradually eject most objects into intergalactic space. When two objects pass near each other, they exchange momentum gravitationally. One speeds up, one slows down. The one that speeds up gains energy and might achieve escape velocity getting ejected from the galaxy. The one that slows down falls deeper into the galaxy's gravitational potential. Over trillions of years, this process called gravitational slingshot ejects about 90% of objects from galaxies. They drift off into intergalactic space, isolated, cooling, never to interact with anything again. The remaining 10% fall toward the center of the galaxy, where they either collide and merge, or orbit the central supermassive black hole. So by about 10 to the 30 power years, galaxies have largely evaporated. Most stellar remnants are isolated in intergalactic space. A few have merged or been captured by black holes. And speaking of black holes, they're the longest-lived objects in the universe. White dwarfs cool down, but don't disappear. Black dwarfs just sit there forever unless something happens to them. Black holes, paradoxically, eventually evaporate. This was discovered by Stephen Hawking in 1974. Hawking showed that quantum effects near a black hole's event horizon cause it to emit radiation. This became known as Hawking radiation. Here's how it works. In quantum field theory, empty space isn't truly empty. It's filled with quantum fluctuations where particle-antiparticle pairs pop into existence briefly before annihilating each other near a black hole's event horizon. These quantum fluctuations can be separated. One particle falls into the black hole while its partner escapes. From outside it appears the black hole is emitting particles. This radiation carries away energy which must come from the black hole's mass via E equals mc caret superscript 2. So the black hole slowly loses mass. It evaporates. The rate of evaporation depends on the black hole's mass. Larger black holes evaporate more slowly than smaller ones. A black hole with the mass of the Sun would take about 10 to the 67 power years to evaporate completely. That's 10 million trillion years. A timescale so vast it's almost meaningless. For comparison, the universe's current age is about 10 to the 10 power years. Supermassive black holes at galaxy centers with masses millions or billions of times. The Sun's mass will take even longer. A billion solar mass black hole evaporates in about 10 to the 100 power years. 10 duodecillion years. There's no physical intuition for time scales this long. The entire history of the universe from Big Bang to now is less than a single moment compared to these time scales. But eventually even supermassive black holes evaporate. Their final moments are dramatic. As a black hole loses mass, its temperature increases and it radiates faster. The evaporation accelerates. In its last second, a black hole releases as much energy as billions of nuclear bombs. A final flash of gamma rays. Then nothing. The black hole is gone, converted entirely into radiation that spreads into space. So by about 10 to the 100 power years, all black holes have evaporated. What remains? Isolated black dwarfs drifting through expanding space. Perhaps some neutron stars and white dwarfs that weren't captured by black holes. Photons, the light and heat radiated by everything that ever emitted light, now redshifted to extremely long wavelengths and low energies. Neutrinos left over from various nuclear reactions and supernova explosions and dark matter. Whatever it is, still present but spread incredibly thin. Everything is cold, approaching absolute zero. Everything is isolated, separated by distances that dwarf current intergalactic scales. The observable universe at this point would be vastly smaller than it is now because accelerating expansion has pushed almost everything beyond the cosmological horizon. An observer, if any could exist, would see only the immediate local vicinity. Maybe a few nearby black dwarfs within 1 trillion light-years. Everything else beyond detection. But we're not done yet, because there's one more process that might occur. Proton decay. In the standard model of particle physics, protons are stable. They don't decay spontaneously. An isolated proton could exist forever. But some theories beyond the standard model, particularly grand unified theories, predict that protons do decay, just extremely slowly. If protons decay, they have a lifetime of at least 10 to the 34 power years. That's the current experimental lower bound. We've looked for proton decay in large detectors containing trillions of protons, and haven't seen any decay in decades of observation. This puts constraints on how fast protons can decay. But it's possible they decay with a lifetime of 1036 power years, or 10 to the 40 power years. We wouldn't have detected that yet. If protons decay, then all matter eventually breaks down. Black dwarfs are made of atoms, which are made of protons, neutrons, and electrons. Neutrons outside atomic nuclei are unstable, decaying in about 15 minutes. But neutrons inside nuclei are stable, held together by the strong nuclear force. However, if protons decay, neutrons will also decay shortly afterward because the nucleus becomes unstable. So, a black dwarf would slowly dissolve as its protons decay one by one over time scales of 10 to the 40 power years. Every black dwarf would completely vanish, converted into lighter particles like positrons, neutrinos, and photons. These particles would spread into space, contributing to the background radiation. At this point, matter in the conventional sense no longer exists. No atoms, no nuclei, no stellar remnants. Just a thin soup of photons, neutrinos, electrons, positrons, and whatever dark matter is all spread across infinite expanding space at temperatures incomprehensibly close to absolute zero. The universe has reached heat death, maximum entropy, complete thermal equilibrium. No differences anywhere, no gradients, no concentrated energy. Nothing can happen because there's no energy differential to power any process. This is the ultimate fate of the universe in the most likely scenario. Not a dramatic ending. No big crunch or big rip. Just a slow fade into cold, dark, empty equilibrium. And here's the profound part. From the perspective of someone at the beginning, from the Big Bang, the universe seems to exist for about 10 to the 40 power years. That's the time scale until proton decay finishes dissolving everything. But from the perspective of the universe itself, from the initial Big Bang singularity to the final equilibrium state, the vast majority of that time is spent in the equilibrium state. The interesting part, the part with structure in stars and galaxies and life, is just the first tiny fraction. 10 to the 14 power years of star formation. 10 to the 30 power years of stellar remnants cooling. 10 to the 100 power years of black hole evaporation. Then infinity or near infinity in the equilibrium state. The entire history of the universe that we can relate to, everything that's ever happened or will happen that we consider significant, occurs in the first 10 to the 100 power years. After that, it's just empty space expanding forever. No more events, no more changes, no more history. The universe doesn't end so much as it stops doing anything interesting. And even those time scales 10 to the 40 power years or 10 to the 100 power years are incredibly brief compared to eternity. If the universe truly exists forever, and there's no reason to think it won't in this scenario, then almost all of time is spent in that final equilibrium state. The era of structure and complexity, the era where we exist, is an infinite decimally brief flicker at the very beginning. We exist in the first moment after the Big Bang, cosmologically speaking, a moment of disequilibrium before the universe settles into eternal equilibrium. This is what makes the emptiness terrifying. It's not just that the universe is mostly empty now. It's that emptiness is the final state. The state that will persist forever. Fullness, structure, complexity, all temporary. Emptiness is permanent. But we're not there yet. We live in what's called the stelliferous era, the age of stars. This era began a few 100 million years after the Big Bang, when the first stars formed. It will continue for trillions of years as stars are born, live, and die. We're about 1% of the way through this era, perhaps even less, depending on how long star formation can continue. The universe is approximately 13.8 billion years old. Stars will continue forming for at least another 100 trillion years, possibly much longer in the smallest red dwarfs. So while the universe is mostly empty now, it's actually in one of its fullest states relative to what came before and what will come after. There are more stars and galaxies now than there were 1 billion years ago. And there will be more stars in the future formed from gas in existing galaxies, until the gas is exhausted or scattered by expansion. So this moment in cosmic history is uniquely rich, uniquely complex, uniquely full of structure. And the most remarkable structures are galaxies themselves. Galaxies shouldn't exist, not in the way they do. Let me explain why this is such a profound mystery. When you look at a galaxy, you're seeing hundreds of billions of stars held together by gravity, orbiting a common center in a relatively organized structure. Spiral galaxies have beautiful spiral arms where young stars are forming. Elliptical galaxies are smooth, featureless clouds of old stars. Irregular galaxies are chaotic, but still coherent structures. All of this implies that galaxies are stable, that their stars have had time to settle into organized orbits, that the structure can persist for billions of years. But the universe is only 13.8 billion years old, and galaxies formed relatively early, within the first billion years after the Big Bang. Some of the oldest galaxies we observe with the James Webb Space Telescope appear to be massive, well-formed galaxies existing only a few 100 million years after the Big Bang. This is shockingly fast. Gravity works slowly. To form a galaxy, you need gas to collapse under gravity into a dense cloud. Then, that cloud fragments into smaller clouds that become stars. Those stars orbit the galaxy's center. Their orbits determined by the galaxy's total mass distribution. Over many orbits, stars interact gravitationally. Their orbits evolve, and the galaxy settles into a stable configuration. This should take many orbital periods. In the Milky Way, an orbit around the galactic center at the Sun's distance takes about 230 million years. Stars closer to the center orbit faster. Stars farther out orbit slower. But it should still take many orbits for the galaxy to settle down. 10 orbits, 20 orbits, maybe 50 orbits. That would be 5 billion to 10 billion years. Yet, we see well-formed galaxies existing only a few 100 million years after the Big Bang. They seem to have formed almost instantly on cosmic time scales. How? Part of the answer is dark matter. Dark matter doesn't interact with radiation, so it can collapse quickly without being slowed by radiation pressure. Dark matter halos form first, creating gravitational wells. Normal matter falls into these wells, concentrated by the dark matter's gravity. This speeds up galaxy formation significantly. Without dark matter, galaxies would take much longer to form, possibly so long that the window for star formation would close before galaxies became stable. But even with dark matter, there are mysteries. Why are spiral galaxies so organized? Spiral arms are patterns where star formation is enhanced by density waves traveling through the galactic disk. Gas clouds compress when they enter a spiral arm, triggering star formation, creating bright young stars that define the arm's visible structure. But spiral structure should be unstable. Differential rotation where inner parts of the disk orbit faster than outer parts should wind spiral arms tighter and tighter until they disappear. This is called the winding problem. Yet spiral galaxies maintain their spiral structure for billions of years. The leading explanation is that spiral arms aren't material structures. They're density waves. Like sound waves or water waves, the pattern moves, but the material doesn't. Stars and gas move in and out of spiral arms as they orbit, but the arms themselves persist as patterns in the density distribution. This works mathematically, but requires specific conditions in the galaxy's disk. The disk needs to be the right mass, the right size with the right distribution of stars and gas. Too massive or too lightweight and spiral structure can't persist. Why do so many galaxies have these conditions? We don't fully know. Another mystery is galaxy rotation curves. When astronomers measure how fast stars orbit at different distances from the galactic center, they find something unexpected. In the outer regions of galaxies, stars orbit much faster than they should based on visible matter alone. This is the primary evidence for dark matter. But the distribution of dark matter needed to explain the rotation curves is very specific. Dark matter forms a roughly spherical halo around each galaxy with a particular density profile. Dense at the center, gradually less dense moving outward. This profile, called the NFW profile after the physicists who discovered it, emerges naturally from computer simulations of dark matter collapse. But why does nature consistently produce this particular distribution? And why does the dark matter halo exactly match the visible galaxy in ways that produce stable rotation curves? It's like the dark matter knows what the visible galaxy is doing and adjusts itself to keep everything stable. Of course, dark matter doesn't know anything. It's interacting purely through gravity. But the fact that these two components, dark matter and normal matter, work together so perfectly to create stable galaxies is remarkable. It suggests something deep about how structure forms in the universe, something we don't fully understand yet. Then, there's the problem of galaxy masses. Galaxies come in a huge range of sizes, from dwarf galaxies with 10 million stars to giant elliptical galaxies with 10 trillion stars. That's a factor of 1 million difference in mass. Why this particular range? Why not galaxies with only 1,000 stars or galaxies with 1 quadrillion stars? The answer seems to be that smaller structures can't hold together against various disruptive processes. Supernova explosions, stellar winds, radiation pressure from young stars. All these can blow gas out of small galaxies. If a galaxy is too small, it loses its gas and can't form new stars. It fades away or gets absorbed by a larger neighbor. On the large end, there seem to be limits to how big galaxies can grow. The largest galaxies form in the centers of massive galaxy clusters through mergers. They're enormous, containing trillions of stars. But even they have limits set by the amount of matter available in their region and by the expansion of the universe, preventing more distant matter from falling in. So the range of galaxy masses we observe is set by physical processes that favor certain scales over others. But the details of why galaxies exist in the forms they do with the properties they have remain active areas of research. Computer simulations can produce galaxies that resemble real ones, but only with careful tuning of parameters, and observations keep revealing surprises. The James Webb Space Telescope is finding massive galaxies in the early universe that shouldn't exist according to our models. They're too massive, too well-formed, too quickly after the Big Bang. Either our models are missing something about how galaxies form, or there's some new physics we don't understand. This is exciting for astronomers, because it means we're still discovering how the universe works. But it also means galaxies are even more remarkable than we thought. They're not inevitable structures that form easily. They're finely balanced systems whose existence depends on multiple factors being just right. Dark matter providing gravitational scaffolding. Initial density fluctuations being the right amplitude. Star formation processes converting gas into stars at the right rate. Feedback from supernovas and black holes regulating how much gas remains. Merges and interactions between galaxies redistributing matter. All of this has to work together to produce the galaxies we see. Change any one factor significantly, and galaxies would be very different or might not exist at all. This brings us back to the anthropic principle. We observe galaxies to exist in forms conducive to star formation and planet formation and life, because if they didn't, we wouldn't be here to observe them. But it's worth appreciating how special this situation is. The universe could have been more uniform with no density fluctuations producing no structure, or more clumpy with fluctuations so large that only black holes formed. Or expansion could have been faster, preventing matter from clumping at all. Or dark matter might not have existed, slowing structure formation so much that galaxies never formed before the era of star formation closed. Any of these scenarios would have produced a universe without galaxies, without stars, without planets, without life. The fact that we exist to observe galaxies means we live in one of the rare configurations of initial conditions that produces structure. And even within that rare configuration, we exist at a special time. Early enough that galaxies are still forming and evolving, providing dynamic environments for star formation. Late enough that several generations of stars have lived and died, producing heavy elements needed for planets and life. Not so late that expansion has isolated all galaxies beyond observation. This is our cosmic context. A brief window in a vast universe where structure exists and can be observed. We live in an era when the universe still has structure. When galaxies are close enough to observe each other, when stars are common enough that planets can orbit them and life can arise. In the deep past, the universe was too hot and dense for structures to form. In the deep future, it will be too cold and empty for anything to happen. We live in the narrow window between these extremes. A window that will close eventually as expansion and entropy do their work. And yet, for all this talk of emptiness and isolation and eventual heat death, there's something remarkable about the present. The fact that we exist at all is extraordinary beyond measure. The fact that matter clumped into galaxies, that stars formed, that at least one star created planets, that at least one planet developed life, that life evolved intelligence, that intelligence built civilizations capable of studying the cosmos and understanding its past and future. All of this happened in an overwhelmingly empty universe that's getting emptier all the time. Consider what had to happen for us to be here. The Big Bang had to occur with exactly the right initial conditions. Inflation had to happen, smoothing the universe and creating quantum fluctuations of exactly the right amplitude. Dark matter had to exist in exactly the right abundance. Dark energy had to exist, but with exactly the right strength, not so strong it prevented structure formation. The density of matter had to be exactly right, allowing galaxies to form, but not collapse into black holes. Stars had to form and evolve, creating heavy elements through nuclear fusion. Those stars had to explode as supernovas, scattering heavy elements into space. Second-generation stars, like the Sun, had to form from gas enriched with these heavy elements. Planets had to coalesce from the debris around these stars. At least one planet had to be in the habitable zone, the right distance from its star for liquid water. That planet needed a stable climate for billions of years. While life evolved from chemistry, life had to survive countless extinction events, asteroid impacts, climate changes, volcanic eruptions. Evolution had to produce increasingly complex organisms over billions of years. Eventually, intelligence emerged. Consciousness capable of abstract thought and scientific inquiry. That intelligence had to develop language, writing, mathematics, science, technology. Civilizations had to arise that valued knowledge and invested resources in understanding the universe. Telescopes had to be built, observations made, theories developed and tested. Every step in this chain was improbable. Any one of them could have failed. If the density fluctuations had been slightly different, galaxies might not have formed. If dark matter didn't exist, structure formation would have been too slow. If dark energy was stronger, expansion would have prevented galaxies from collapsing. If the Sun had been slightly more massive, it would burn too fast and die before complex life could evolve. If Earth had been slightly closer to the Sun, it would be too hot for life, slightly farther, and it would be too cold. If Jupiter didn't exist, asteroid impacts on Earth might have been so frequent that complex life never had time to develop. If the Moon didn't exist, Earth's axial tilt would vary chaotically, preventing stable climates. Every detail matters. Change any one thing, and we might not be here. This is sometimes called the fine-tuning problem. The universe appears finely tuned for life, with many parameters set to exactly the values needed for complexity to arise. Some physicists interpret this as evidence for design for a creator who set the parameters deliberately. Others invoke the multiverse, the idea that there are countless universes with different parameters, and we necessarily find ourselves in one where conditions permit life. Others point out that we're still early in understanding physics, and we might discover deeper principles that explain why parameters have the values they do. All of these perspectives have merit, and none are conclusively proven. But regardless of interpretation, The fact remains that we live in a universe hospitable to complexity and consciousness. And that universe is mostly empty. The emptiness isn't a bug. It's a feature. It's a necessary consequence of the conditions that allow structure to form. Too dense and everything would collapse into black holes. Too empty and gravity couldn't pull matter together into galaxies. The universe had to be exactly this empty to produce galaxies and stars and us. And it's getting emptier because dark energy is accelerating expansion, isolating structures from each other. But this process takes trillions of years. We exist in the era when the universe is full enough to observe and study. When there are still galaxies visible in our telescopes, when the cosmic microwave background is still detectable, when we can still piece together the universe's history and predict its future, this era won't last forever. Eventually, the observable universe will shrink to just our local group. Then eventually, even our own merged galaxy will be the only structure visible. After that, on time scales beyond comprehension, even our galaxy will dissolve as stars burn out and black holes evaporate. Heat, death, maximum entropy, maximum emptiness. But that's trillions of years away. For now we're here. We're conscious. We can observe and understand. We're a temporary pattern in matter and energy, emerging briefly before dissolving back into the void. But while we exist, we can observe, we can measure, we can understand. We can look at the emptiness and calculate why it's empty. We can measure dark matter even though we can't see it. We can detect dark energy even though we don't know what it is. We can trace the universe's history from the Big Bang to the present and project forward to the far future. This ability to comprehend our situation, to grasp the scale and structure and fate of the universe is perhaps the most remarkable phenomenon in all of nature. Consciousness arising from matter, observing itself, understanding itself, recognizing its own impermanence, and doing so in a universe that is fundamentally, profoundly, terrifyingly empty. We are islands of complexity in an ocean of void, temporary structures in an expanding universe, brief moments of order in a cosmos trending toward disorder. But we're real. We're here and we understand why. That understanding doesn't change the physics. It doesn't stop the expansion or prevent the heat death, but it transforms the meaning of emptiness. An empty universe that's never observed remains just empty. An empty universe that's observed and comprehended becomes something more. It becomes context, backdrop, the stage on which the drama of existence plays out. And the emptiness itself becomes meaningful because it explains why we're rare, why we're special, why this moment matters. If the universe were full, if galaxies were packed together like grains of sand on a beach, our existence wouldn't be remarkable. But they're not. Galaxies are separated by millions of light years of emptiness. Most of space contains nothing. And that makes the parts that do contain something, the thin filaments where galaxies cluster, the rare places where stars shine and planets orbit profoundly significant. We exist in the exception, not the rule. In the rare pockets of density scattered through vast emptiness. And we're conscious of that fact. We understand that we're rare, that our existence is improbable, that the emptiness surrounding us is the norm, and we are the exception. This knowledge should change how we see ourselves and our place in the universe. We're not central, not privileged by location or importance. We're not the purpose of creation. The universe wasn't made for us. It just happens to have conditions in certain rare places at certain rare times that allow complexity like us to exist. But that doesn't diminish our significance. It enhances it because we're the universe's way of knowing itself. The rare places where matter organizes into structures capable of observation and comprehension. Where physics gives rise to chemistry, chemistry to biology, biology to consciousness, consciousness to science. Where the universe looks back at itself and understands why it's empty. The universe is empty for reasons we now grasp. It started nearly uniform with only tiny density variations. Those variations amplified over billions of years into the structures we see today. But expansion was always working against structure formation. And now with dark energy driving acceleration, expansion is winning decisively. Structures are dissolving, voids are growing, and the observable universe is shrinking. In the far future, everything will be isolated, disconnected, frozen, dark, heat, death, the final state of maximum entropy and maximum emptiness. But right now, in this brief moment between the Big Bang and heat death, the universe has structure. It has galaxies and stars and planets. It has life and consciousness and curiosity. It has us looking up at the sky, measuring the distances between galaxies, calculating the density of matter, inferring the presence of invisible dark matter and dark energy, tracing the cosmic web of filaments and voids, understanding how it all came to be and where it's all going. The universe is empty. Yes, terrifyingly, profoundly, overwhelmingly empty. Almost everything is nothing. Almost all of space contains almost no matter. And what matter exists is mostly invisible, mysterious, understood only through its gravitational effects. The voids are vast, the distance is incomprehensible, the isolation absolute and increasing. Dark energy is tearing space apart, accelerating expansion, pushing everything away from everything else. The cosmic web is dissolving. Structures are fading. The lights are going out one by one. Entropy increases. Order decreases. Complexity gives way to simplicity. The universe is running down, cooling off, spreading out, approaching its final equilibrium state. But in the small fraction of space that does contain visible matter, in the thin filaments where galaxies cluster, in the rare regions where stars form, in the vanishingly unlikely places where planets orbit at just the right distance for life to arise, something extraordinary happens. Matter organizes itself into increasingly complex forms. Atoms become molecules. Molecules become cells. Cells become organisms. Organisms become conscious. And consciousness looks back at the universe and understands it. That understanding doesn't change the emptiness, doesn't reverse the expansion, doesn't prevent the eventual heat death, but it gives the emptiness meaning. Because an empty universe that's observed and comprehended is fundamentally different from an empty universe with nobody to notice. We are the universe noticing itself. Brief sparks of consciousness in an ocean of darkness. Temporary patterns in an expanding void. But we're here now, and we understand why the universe is empty. And that understanding, that ability to grasp the terrifying physics of cosmic emptiness while existing as complex structures within it, that's not nothing. That might be everything that matters in this brief moment before the darkness returns.